Hello. Sorry I could not be there. I will be back later today, but your notes must go on, and that's why they're coming to you via video. Today we're going to divide segments proportionally, and we'll start off with our most basic way to divide a segment in proportion, which would be 1 to 1, and that's using our midpoint formula. So we'll also divide segments not only in 1 to 1, we'll do things like 1 to 3, 1 to 4. We'll even divide segments in fractions. So I want to locate a point on this line segment that is 2/5 the way along the line, and so forth. Okay, so that's what we'll get into. But we're going to start off nice and basic with essentially just dividing things in half. So using our midpoint formula. So remember, our midpoint formula is the average of our x's and the average of our y's. So x1 plus x2 over 2, y1 plus y2 over 2. And again, that's used to divide our line segment. If I called that m of AB in a ratio of 1 to 1. So 2 total equal parts. So the midpoint formula can be used to find the midpoint of a segment. Finding the midpoint divides it into a ratio of 1 to 1. So in our picture below, I have points A and B. So A is at -4, 5, B is at 12, 13. I'm going to find the midpoint M of AB. So I'm simply going to add the x's, divide by 2, add the y's, divide by 2. So I'm getting the point 49, which I'm going to go ahead and plot. Okay, that's our midpoint. And we can say that it divides the segment AB in the ratio of 1 to 1. Okay, if you were to, even just by visual inspection, figure out where that midpoint is, it has to do with the fact that if you were to create a right triangle out of this and take this segment and locate its midpoint, and take this segment and locate its midpoint, they would intersect at that location. Okay, and it has to do with these two triangles being congruent. So that's just another visual inspection of how you could locate that midpoint. Okay, and the reason I'm drawing these triangles is because when I get into harder problems, you're going to see me use this idea of dividing this in half, or dividing into a third, we'll say, and using that concept to locate a new point. Okay? I'm just going to erase that for now. Okay, so that's our point. So it's pretty easy to find a midpoint given 2 points of the end points, but what if I gave you a point A, which is 1, 1, and the midpoint 5, 6. And I want you to find the other endpoint, B. Okay, so I'm just writing an extra example here. A is 1, 1. And M is right here at 5, 6. And B is unknown. You have to think that B is equidistant to M as A is to M. So in order to get from 1 to 5, I'm noticing my x's are changing by 4. So I'm going to do the same thing to figure out the x coordinate of B. I'm just going to add 4. So that would give me 9. From 1 to 6, it looks like we're going up by 5. So I'm going to do the same thing. I'm just going to add another 5. So 6 plus 5 is 11. So by using this idea that my x's and y's would have to change by the same amounts, because M is the midpoint, allows me to find now the other missing endpoint. Alright, so let's get into a little bit of harder examples. I'm going to find point C that partitions the segment AB with endpoints A, B in a ratio of 1 to 3. I want you guys to think about that as 4 total equal parts. Okay, so I'm going to go ahead and just graph this so we see what we're working with. So A is at negative 3, 1. B is at 5, 5. And that's our line segment. Okay. The first location for C that I'm going to find is one that's closer to A than it is to B. So what that means is, opposed to being 1 to 3 that way, I'm going to be 1 part for another 3 parts. So 4 total equal parts in this direction. So C is going to be closer here. It's going to be in this vicinity. Okay. So if we're breaking it up into 4 equal parts, we could actually just use our midpoint formula a couple of times. So the first thing I'm going to do is find the midpoint of AB. Okay, so I add my x's, add my y's, divide by 2, and I would get 1, 3. Even just by visual inspection, you guys should be able to see that that would be our midpoint. Okay, so then if I want to find how this would break up into a fourth, I would just take the midpoint again. So if I find the midpoint of AM, AM, halfway in between A and M would be right here at negative 1, 2. So that is your first possible location for C. So I'm just going to call that C1. At part B here, it says now I want C so that it's closer to B than it is to A. So technically now the ratio is backwards. It's going to be 3 equal parts to 1 part. So I would then find the midpoint of MB. So you could either do it with add your x's, add your y's, divide by 2, or just by visual inspection, you can kind of see using the slope that these two triangles would split that up nicely into 2 equal parts. And this would be your second possible location for C2. And that's at 3, 4. Okay, so that's how using the midpoint can be pretty easy to help break the segment up not only into 2 equal parts, but into 4 equal parts. And then I can do the appropriate ratios. So 3 to 1 or 1 to 3. Okay? All right, so let's move on to question 3. Find point C on the directed segment from A to B that divides a segment in a ratio of 1 to 7, with C being closer to B. All right, so A, if I had to plot it on the grid, an invisible XY axis would be roughly over here. Because then a negative 4, 5. B would be way over here at 12, up here at 13. So there's my directed line segment. I'm going to break it up in the ratio of 1 to 7, where again we said C was going to be closer to B than it is to A. So 1, 2, 7 that way. This is 8 total parts. So my first thing is I'm thinking, well, I could break it into halves, which would then break into fourths, which would then break into eighths. So I can first find this midpoint by adding the x's together, dividing by 2, adding the y's together, dividing by 2. Okay, so this is my first midpoint of AB. So that's 12 plus negative 4, so that is 8 divided by 2, and then 13 plus 5, so that's 18 divided by 2. So that gives me 4, 9. So I'm going to label that. Okay, so this is like my halfway mark. Okay, and find the next halfway mark. So that would be halfway in between 4, 9 and 12, 13. So that's 4 plus 12, which is 16 divided by 2. 9 plus 13, so that is 22 divided by 2, and that gives me 8, 11. Okay, so that would be like my quarter mark. So that would be, this would be a quarter, that would be a quarter, and then I could break this up into quarters as well. So this is my quarter mark. I just need to go one more. I need to find this point right there, and that's going to be my location of C, which obviously when I sketched out my ratios, it didn't work out quite nice. There's my 1. That's my 7. So now I'm going to find the halfway mark between 8:11 and 12:13. So 8 plus 12 is 20 divided by 2. 13 plus 11 is 24 divided by 2. So that's 10, 12. And that's your location for C. Using the midpoint formula over and over again is really pretty easy. But what if I want you to divide the segment into sixths? That's where things get a little bit tricky. So let's say I want to find point C on the directed line segment from A to B that divides it into a ratio of 1 to 5. So that's 6 total parts. And I'm going to have C closer to A. So if I were to plot where A is, okay, and I'm going to actually sketch out an XY axis here to help me. We will say that A is like roughly over here. B is 12, -1, like roughly here. I just need like a general idea of where it is so that I know the direction of the segment. So I'm going to find C so that it's closer to A in a ratio of 1 to 5. So 1 to 5, so that's 6 total parts. Now here's where I'm going to create a right triangle, similar to what I did or kind of showed you in the beginning with locating the midpoint. Okay, I'm going to draw this triangle going down. I could do it going up, but I'm just going to go down. So here's my right triangle. C is going to be somewhere in this vicinity. Okay, I don't know exactly what it is. I'm just going to say C somewhere in here, and I'm going to draw a line down. What I want you to focus on, and this is going to really relate to our similar triangles, is I have created 2 similar triangles. I have this little guy in here, and this big guy. Okay, those are similar. Okay, this purple triangle that I have in the middle here is 5/6 the size of the big triangle. So each of the sides, I should say, each of the side lengths is 5/6 the size of the big triangle. So if I can use that scale factor, so I'll write that down, it'll allow me to help locate this point C. Okay, so essentially what I'm going to do is I'm going to take this big triangle and dilate it by a scale factor of 5/6. That would give me this purple triangle. And that'll help me locate this coordinate point by helping me find these 2 side lengths. So this horizontal distance, that's along your axis, right? So that's always going to be the change in x between these coordinates. So the difference between -3 and 12 is 15. It's that positive distance if you were to count those units. Okay? This part is your up and down, so that's your change in y. So that's the difference between 11 and -1. So that's 12. Okay, so in order to figure out each of these new lengths of this similar triangle, I'm going to take the big triangle, or my pre-image, and multiply it by the scale factor I need, which would be 5/6. And notice it's because I'm using this as my center of dilation, -12 or 12, -1. So I go ahead, I do 15 times 5/6, and I get 12.5. Okay, I'm going to do the same thing with this. I'm going to take 12, dilate it by 5/6. So 12 times 5/6 would give me 10. Okay, so what that means, again, is that this length here is 10. This length is 12.5. Now, how does it help me find that coordinate? Well, follow the translation. This is a point that I know. From the center of dilation, if I go back 12.5 and up 10, that would help me locate that missing point. Okay? So from 12, negative 1, so that's my center of dilation here that I'm using. I can go back or subtract from my x's, 12.5. And then I'm going up. So that's an increase in my y. So I'm going up 10. So that means that this missing coordinate C is negative 0.59. Okay, and that's how I use similar triangles and translations, so many concepts that we've talked about before, to help me locate my missing point. Okay, let's try another one. Find a point on the directed line segment AB that divides it in a ratio such that AC to CB is 2 to 3. Okay, so just like the last example, I'm going to sketch what this looks like. So this is my x and y axis. A is at 6, 3, so maybe like here. And B is at 1, 8. Okay, it's at AC to CB is 2 to 3, so that's 5 total parts. And since it's 2 to 3, so A or C to A is 2, that's your shorter part. So that means A is closer, or C is closer to A, I should say. So C is like roughly in here, we'll say, okay? 2 to 3, 2 to 3, AC to CB. That's 5 total parts. Okay, so just like the last example, I'm now going to create a right triangle. 2 right triangles, actually. A is going to be your center of dilation. The scale factor is 2/5. That's because I'm just measuring the distance to that center of dilation based on the ratio, which is 2, in comparison to in the big triangle, which is 5. So I'm not using the 3 here because that's not a part of the smaller triangle. So I'm going to go ahead and figure out each of these side lengths of my bigger triangle, and then I'm going to use the scale factor of 2/5 to help me. Okay? So this horizontal distance would be the change in my x's between A and B. So between 1 and 6, that's a distance of 5, or a difference of 5. The up and down is the change in my y's. So that's the difference between 8 and 3, which happens to also be 5. Okay? So that means that this new distance right here is going to be the pre-image of 5, but then dilated by a scale factor of 2/5. So 5 times 2/5 is just 2. Okay? And it's actually going to end up being the same thing here, and that's just because this y distance is 5 as well. So I'm taking 5, I'm going to dilate it by a scale factor of 2/5. That gives me 2. And now I'm going to use that to apply the translation. So from A, you're going back 2, up 2. So from that, so x would be back 2 would be subtract 2, up 2 would be plus 2 on my y's. So that means my missing point C is 4, 5. Okay. Given points PQ, find R on PQ such that PR to RQ is 7 to 3. This is just another way of saying it as we've been seeing it, 7 to 3. So this is 10 total parts. Okay, so P is way over here at 10, 10. Q is over here at 0, 4. So now I have my directed line segment going the other way. That's okay. It's still going to be the same process. Okay, so it says PR to RQ. So RQ is the smaller part, right? So that means R is going to be closer to Q. So I'll just put R there. Okay. I'm going to create a right triangle by drawing the triangle down. So it's just facing the other direction. That's okay. There's your second right triangle. Okay, so again, this is breaking up. I'm going to move this a little bit. That 0, 4 was going to get in my way, and it was going to annoy me. All right, so this portion is your 3. That's your 7. So this is 10 total parts. So from the center of dilation, this small triangle is 3/10 the size of the big triangle. So my scale factor I'm going to use here is 3/10. Okay. The big triangle is, again, the change in your x from side to side. So from 0 to 10 is just 10. The up and down is your change in y. So that's from 4 to 10, which is 6. That means that this little portion right here is 10, so the pre-image, dilated by a scale factor of 3/10. So that would just give me 3. Okay, so this is 3. This vertical portion is going to be the pre-image, so the 6 dilated by 3/10 as well. So, sorry, whoopsies. So 6 times 3/10 is 1.8. Okay, so now I'm going to apply the translation. I'm going to start from my center of dilation, which is Q. From there, to get to R, I'd have to go to the right, which would be adding on your x's, 3, because that's how long this distance was, 3. So I'm going to add 3 to my x's, as opposed to subtract, right? That's when I was going backwards. Now I'm going forwards. Then I'm going up. So that would still be adding on my y's. So I'm going up by 1.8. So my missing point R is going to be at 3, 5.8. Okay, so I hope you guys are seeing all these connections going back to Unit 7 with our center of dilation, our scale factor, image and pre-image, and applying these translations from Unit 4. As we always joke, all the stuff in this course is interconnected. All right, so now I'm just going to phrase it a little bit differently. Given points A, B, find the coordinates of point C so that it sits 2/5 of the way along the segment AB, closer to A than it is to B. So now this is no longer a ratio. This is of 5 equal parts. You're going to be 2 of those parts along the way. Okay? So A would be like down here, -4, 5. B would be up here at 12, 13. There's my segment. Okay, so closer to A than it is to B, so let's just say our missing point is right there, C. Okay, so I'm going to move this for a second. I don't like how that looks. Instead of doing 2, 5, because that would be a ratio of 2 to 5, and that would imply 7 parts, this is just 2/5 of one whole part. So this is 2/5, and then technically this is 3/5. Again, this is one total segment. Okay? I'm going to create a right triangle. There's my other right triangle. This is still my center of dilation. My scale factor, if you want to think about it as still like circling stuff, is still going to be this, technically over 1, but over 1 is just itself. Okay, so I'm just going to multiply each of these side lengths of the larger similar triangle by 2/5, and that will help me locate this missing point. So again, horizontal distance would be change in x. So from -4 to 12, that's a distance of 16. Horizontal distance would be from 5 to 13, so that's 8. This portion right here is going to be 8 times 2/5. So that's 16 divided by 5, so that's 3.2. This distance right here is then 16 times 2/5, so that's 6.4. Now we apply the translation. So from A, from our center of dilation, which was again negative 4, 5, we're going to the right 6.4, so that would be adding 6.4 on my x's, and then going up 3.2. And that gives me my location of C. Lost control of my pen there for a second. Alright, I'm going to do one more. Same points, but now it's going to be closer to B than it is to A. Okay, so same drawing. But C's now here. So that means the 2/5 is here. The 3/5 is here. So when I draw the triangle, you'll notice that you'll notice that this smaller triangle actually looks a little bit bigger than the previous one, which makes sense because it's 3/5 the size of the whole segment as opposed to 2/5. So again, this is still out of one whole segment, because we're talking about a fraction of a segment. The scale factor is now instead going to be 3/5. Okay, now here's the good news. We already know that this distance here is 16, and we already know this is 8. That's because we calculated it in the last problem. So then, if I want to figure out what each of these side lengths is, instead of doing by 2/5, I'm going to do by 3/5. So 16 times 3/5 gives me 9.6. 8 times 3/5 would give me 4.8. Now I apply the translation. I'm going to the right and up. So that means I'm adding 9.6 to my x's, adding 4.8 to my y's. And that's it. Okay, so I will be back next week to answer questions about this. The good news is about this video, the good news about this video is that you guys can rewatch it and use it to help you. So if you thought maybe something moved too fast and you're confused, or maybe you need to listen or just see me do this one more time to explain it, you're going to have this video forever. All right, see you later.